So this will be a continuation of Hess's law, and it will be particular to a certain application of Hess's law. So our objectives, we're going to define the heats of formation, which are delta H sub F, and then we'll review Hess's law, and we'll learn how to use Appendix G, which will become your friend in this section, and we'll apply Hess's law to problems with heats of formation. So what is a heat of formation, or delta H sub F? It's the change in heat when 1 mole of a compound is formed from constituent atoms in their standard state conditions, 1 molar and 1 bar. Note, temperature is not specified. These values are temperature dependent, but we have several temperatures that we use for tables of information of this sort. The one in the back of the book is at 25 degrees Celsius, or standard ambient temperature. But you can also find tables for biological purposes at human body temperature, ones for cold storage calculations at 0 degrees Celsius. You get the idea. The other thing about these standards, 1 molar applies to aqueous materials. Otherwise, the number of moles is equal to the coefficient of the material. So in the example that I have here, we're making water from hydrogen gas and oxygen gas. We conform to this definition. We're making 1 mole of water, so we need only a half a mole of oxygen. Both the hydrogen and the oxygen are in the state they would be at room temperature and at 1 bar, which is roughly room pressure, as is the water. But it turns out there is another delta HF for gaseous water because water vapor is constantly around under these same conditions. So we'll get to the reference tables when we try this problem, or when we try a problem. But for now, let's review Hess's law before we try to do things. We're going to learn a different version of it, which is actually the same thing, but said a different way. So Hess's law, to review, the overall enthalpy change is the sum of the standard enthalpies of reactions into which the overall reaction may be divided. So this is a fancy pants restatement of you just take the sum of all the component things. And on the left here, we have a nice little diagram showing that you can get to the same amount by doing more steps. Now, when we use heats of formation with Hess's law, you are making the chemical species from the elements. So all of the reactants, you have to flip the equation, the heat of formation. When you flip a heat of formation equation, just like we did before, we have to flip the sign of the equation. So therefore, delta H is equal to the sum of the contribution from each of the products minus the sum of the contribution from each of the reactants. And again, that's because you have to flip the heat of formation equation to get what you're looking for in a reactant. So at this point, you are going to be tempted to only remember products minus reactants as Hess's law. But this only applies to working with heats of formation. If you do the version from last time, where you're recombining various thermochemical equations, you will get the wrong answer if you do this. Products minus reactants summarizes what happens when you have to flip all of the reactant heat of formation equations. It has nothing to do with the other thing. This is a summary of how to do the other thing systematically for heats of formation. All right, so let's take a look at a problem. We're going to determine the enthalpy change of this reaction. So we have C6H6 plus 9 halves oxygen makes 6 CO2 and 3 water. And yes, I know you're currently cringing over that fractional amount of oxygen. I assure you it will be okay. The math will still work either way. We're looking for 1 mole of stuff, which is why we did that. All right, so where are we going to get the values for heats of formation? From Appendix G, Standard Thermodynamic Properties for Selected Substances. It's at the end of the book. You can just go to the table of contents and flip down there. Now, we're going to multiply the coefficient times the heat of formation of that particular species and add it to the next one. So overall, we're going to have products minus reactants. Now, if you look carefully here, we have given the phases of each of these materials. And the reason why that matters is that water can be both liquid and gas at room temperature and pressure. So let's go to the table. If we look at the table here, you can see that we have both liquid water and gaseous water. And we want to make sure that we read the correct line. And I know that sounds so stupid, but nothing sucks more than getting to the end of one of these problems where you've looked all kinds of stuff up in the table and discovering that you have in fact looked at the wrong line of the table. So get a straight edge. And by that I mean a piece of paper, you can use your pencil, whatever. Make sure you read the correct line from the table. There are a few things that are more infuriating than looking up a series of values and copying down the wrong line, the one above or below, and getting the wrong answer. Because it's not even like you didn't understand. You just copied it wrong. That sucks. Use a straight edge. All right. So I went ahead and I looked up all of these numbers in the table. You will notice that I distributed the negative sign through the reactants. And when I add all of these up, I get negative 3,268. So I'm rounding to the ones place because 49 kilojoules per mole is to the ones place. This is not super hard. The biggest problem is going to be using the table correctly. I guarantee you that will be what causes you fits. Make sure you're using the correct phase of the material you're looking at. So to summarize, heat of formation, delta H sub F, is the change in heat of 1 mole of a compound is formed from constituent elements in their thermodynamically stable state at room temperature. So that would be, solid, liquid, gas, or aqueous. And Hess's law, when using heats of formation, is products minus reactants.